Okay, so today we are going to continue our question of finding ranks of finite semigroups. Okay, especially what we're interested in is subsets, special subsets or special sub-semigroups of the transformation semigroup. Okay, so that was our initial goal. And to that, we have first developed the theory of simple semigroups because we'll see that will reduce our problem to simple semigroups or completely simple semigroups. Yeah, the same notions for finite case. So yeah, so we have developed that theory. In particular, we have a combinatorial, you could say, a representation, the Rees matrix theorem for completely simple semigroups. So we did that, and then we, like, before actually finding doing the real problem of finding smallest generating sets or ranks for subsets for special subsemi groups of Tn, we just solved the easier problem of finding the rank of Sn, right? We saw that its rank was 2, and also we solved the rank of Tn itself, and we found that it was just 3. So now we want to get into more general business, and to that, we'll first explore the rank function itself and how does it behave in general. Now, well, as you would expect, right, as you would expect, the rank function is not well behaved under taking sub-semigroup. So what does this mean? It means that if you have a semigroup, big semigroup, it may be generated by, let's say, only two things, but then you will find subsets of that or sub-semigroups of that or subgroups of that which will meet more generators. In fact, we will see this very clearly because we will find ranks of sub-semigroups of Tn which will have big ranks, big large number of generators would be needed. um, and this is expected if you look at for example, Tn itself is just generated by 2 or 3 elements, right? So if this were not the case, then every sub-semi group would be generated by 2 things or 3 things, right? Because so we know that every semi group is a sub-semi group of some Tn, at least every finite semi group, right? Yeah, exactly. So obviously it's not well behaved in us undertaking sub-semi groups. Okay, this is in general the feature of rank or generators for, even if you look at ideals, even when you generate something as ideals, which is obviously different from generating something as a sub-semi group or as a, generating something as an algebra versus generating something as an ideal, obviously different. But even there, you know that undertaking sub-semi groups, it doesn't behave well. Okay, so I mean, knowing these features will help us to um, develop more effective strategies, basically. Okay, however, if you look at the second one, this is something which we will use, this quotienting. Uh, so what are we looking at? So you have a subsemi group S, right? So maybe I can draw a picture here, right? So if you have a subsemi group S, okay, and if you have a surjective map from here, okay, so maybe I'll just change this to a little lighter. Yeah, if you have a surjective map from here to another one, right, then what are we saying? We have this S, and let's say this is S1. Now this S1 is basically a quotient. It's going to be a quotient of S if phi is a surjective map, right? It's just that phi adds more relations, and so you get a quotient. It's a quotient. Now we want to claim that the rank of the domain is always bigger. This is not difficult, right? Because it's always bigger than, or it's at least the rank of the range. It's not difficult because let's say these 4 things generate S, then their images would generate S mod, would generate the range, right? These things would generate the range, okay? Because, well, I mean, you look at anything in the range, it comes from something in the domain, and that thing in the domain is generated by these 4 things. So because of the homomorphism, so that's quite easy, okay? But yeah, sometimes this may not go down, and sometimes it might go down. So one has to be careful there. I mean, just thinking, how could this potentially be useful, right? Because the sense is that sometimes S mod, or rather, I should say, the quotient or the image of the surjection, all the different maybe useful ways to think about surjective map phi. The idea is that sometimes the quotient may be a simpler semigroup. It may be simpler, a lot of collapsing might happen, and you may find the rank there, and that might help you to give you lower bounds. Okay. Or if by some other way you know that the rank does not go down, and this is exactly what we'll be doing. We'll be quotient we'll, to find the rank of our some side of some kind of semigroup. We'll be quotienting it, okay. But with some property that will tell us that the rank does not go down, but the quotient would be a simpler, in fact it will be a simple in the precise sense semigroup, and we'll find the rank there, which it will be easier to find, and then we can use that to comment on the rank of S. Okay, this will be very this can be very very useful. Okay, this concept is very useful, and it is sort of used in some in a extremal in sense by the concept of what is known as critical semigroups. So that is like, so just to before we actually get the definition, it's something like this. Okay, you start with a semigroup S, you add some relations, means you take a surjection, and let's say the rank does not go down, right? But your semigroup simplifies. You keep taking surjections, okay, till you reach a subsemigroup, so that you cannot take any more quotients without decreasing the rank. So what does that mean? It means that you have reached a semigroup S, or you have reached a semigroup S1 from S. Okay, you have reached a semigroup S1, which is sort of like the simplest semigroup. I'm not saying the sense of freest, in the sense of having most quotients. It's just kind of the simplest semigroup with that particular rank. So you have preserved the rank, but you have kind of gone to the simplest guy or the extremal guy where you preserve the rank, and that guy, that semigroup which you have reached, is was known as a critical semigroup. Okay, so this is because now obviously what feature would it have? It would mean that any surjection from there on, would lead to decrease of rank. Okay. Now, this can be good because, as I've noted here, S might be the easiest to find the rank among the semigroups with rank S. Okay, that's why it's known as critical. So it's basically the critical point. It's where the situation changes. It's where the change happens. As we know, critical points are useful to get it philosophically. To get it in analyzing functions, or so there is even a concept of what's known as critical graphs. Okay, graphs where you take graphs whose any subgraph would have a lower chromatic number. And so if you want to study graphs with a particular chromatic number, and if you want to study feature of such graphs, sometimes you look at the critical subgraph with that chromatic number. And such critical things always exist because the rank at some point it will go down if you simplify the graph, keep simplifying the graph. So in that sense also, so we know that the theory of graphs that is very useful. We have several inequalities. It means several things which we can say about the chromatic number of a general graph by going to the by going to the critical graph in that class of in that uh, class of chromatic number. Okay, graphs with that chromatic number, and so on. So just saying that this notion of criticalness is a useful notion. So when you're dealing with um, like a big family of things, and you're trying to find ranks, or you're trying to quantify some notion of complexity there in that system, then maybe you could look at the critical members of the family, and maybe that can help you. Okay, so this is very useful. So we'll not be needing this too much, because at least in the first part where we find generators of semigroups of sub semigroups which we're looking at will be based on whose image size is k, let's say, in general. Okay, so there we will not need this too much, but later on, for finding other kinds of sub semigroups based on order preserving and other things, and even in the infinite dimensional case, this can be useful, or I should say infinite semigroups in the sense of cardinality. Okay, so Right, but they of course they may still have finite generators. So that's where this will be useful again. Um, right. So these are the observations about the behavior. Okay. Now we look at more specific to our purposes kind of feature of the rank. Now you see, the goal is to find the rank of semigroups, but we spent a lot of time on simple semigroups. Simple semigroups, I mean, simple semigroups are like J classes, right? They are like one block, one J class. Okay. So we would first, before we say how rank is precisely connected with simple semigroups, or finding rank of a semigroup is precisely connected with finding rank of simple semigroups, at least in our case. Before we get to that, let us get a general sense. I mean, this is the general picture of how finding rank, or at least finding lower bounds, which is what many times one has to um, be happy with. Um, Before more progress is made is so we want to see how lower bounds of ranks, or how finding ranks can be uh, how this problem can be reduced to finding ranks of J classes, something like that. Okay, so for that we will look at maximal J classes. So why are we looking at maximal J classes, right? Because maximal J classes are sort of independent. So it's like if you look at the concept of basis and vector spaces, if you have a vector space and if you write it as direct sums, and the rank kind of distributes precisely, right? So that is what we are trying to do here. Okay, so we will look at, let's say, that k maximal J classes, though again this is full generality, we will not need this, and I mean our case would be um, we will sort of have only one maximal J class. Okay, but still, let's say, but I'm saying that the idea works, and this is, again, this will be used later in harder questions. Okay, so if you have k maximal J classes, then if you want to find the rank of the semigroup, okay, S, okay, the claim is that you can, I mean, the claim is that you don't lose anything if you find the rank of the J classes, the maximal J classes separately. So let's see some picture maybe. So if so, I'm drawing the J classes as boxes, which they are not. If these are, I'm drawing them as D classes because that's what they are in the finite case. They are not like that in general. So let's say there are k of them. These are maximal, and there might be some things in below and so on, whatever. Right. So now we are claiming that if you want to find the rank of S, right, that is at least, I mean, to start with, that is at least the rank of these things. Okay, so why is it like that? Yeah. So the point is that, let's say you want to generate something in J1. Let's say this is J1, this is J2. Let's say you want to generate something here, okay, in J1. And the point is that to generate something in J1, its generator must lie in J1, because if X is not in J1, or if X is not in Ji is a maximal J class, then X times Y will not be in Ji, right? X times Y will sort of, I mean, it will, so how do you think about it? X times Y, if X is not in the J class, if X is not in Ji, then X is lower in a lower J class, or it is in some in some other one of the other maximal J classes, right? Now, when you multiply by Y, either it will remain in that other J class, which is not Ji, or it will go down. Now, when going down means that it will not be maximal, it will not be in a maximal J class anymore. So the conclusion is that if X is not in the maximal J class, then you cannot use it to generate. So the generators must come. So the generators for J1 must come from J1, and a generator for JK must come from JK, and things like that, right? So this this is what says, right, that you need to generate those separately, and so the rank must be at least that. But we will see that usually, now how do you quantify this? But this is, so I'm not trying to defend this claim, but my point is usually equality will hold. Okay, maybe I have not mentioned it, but at least this can help you to find lower bounds. But in natural cases, if the situation is good, then this will usually give you an equality. That's because, well, the sense is that if you are generating the entire semigroup, which means if you're looking at J classes which are below the maximal J classes, then if the situation is good, you will fall down from one of the maximal j classes to that, and so the idea is that you'll sort of be able to generate it from that j class. Okay, but that's not always true, but in most cases it is true. In our case it will be true. In our case we'll have only one j class, right? So right, so that's what we'll be doing, and j classes are simple, right? So this is how simple semigroups come in the picture. Okay, that's what it is. Okay, so that's where we have done. Now what we want to do next is, well, yeah, we we are going to look at again a simpler problem. Okay, and so what we want to look at is very concrete semi groups. Okay, but as we know that our semi groups are special, are going to be, we are going to do our, we are going to find our rank using the by reducing the problem to simple semi groups. So we need to first of all know something about finding ranks of completely simple semi groups, right? So that is what we will try to do now. So we want to find rank of, sorry, so we want to find rank of completely simple semi groups. Okay, and of course we'll first do it for very simple completely simple semi groups. We'll see. Okay, so now we will be using our Rees matrix theorem. So given a completely simple semi group, we can assume that it has a group part. Okay, we know that it is sort of has a group part, and it has these indices which can be used to generate that entire semi group. Okay, plus the multiplication can be captured by a regular matrix P. So this is what we have seen. Now, because we are doing the problem of semi groups, right? What we can do is we can, and this is the only hopeful way to maybe start, in the sense that we want to make this problem completely combinatorial. So for that we'll quotient by the group part. Okay, so what, so this is also a completely simple semi group. Like the, after you quotient by the group part, this is also a completely simple semi group, but the feature is that its group part is just the identity. Okay, so if you want to see this once again, so if you want to, so we know that this completely simple semi group is just 1D class. But the point is that if you look at the group in the corner, it's just one element there, just the identity element. And so all the H classes have only one elements. Okay. Some of those H classes are groups, and the other H classes will be, I mean, the other H classes will be nilpotent. Will be nilpotent. It means not just nilpotent, but elements of square is zero. Null classes. These are the properties which we proved about completely simple semigroups. So the situation is like dichotomous. Either it's a group, or either an H class is a group, or it's completely null. Okay, so that is the point. So here, as you can see, we have quotiented by the group, right? So let us make a definition which kind of formalizing says that formally. That is the definition of relative rank. So what's the relative rank of S with respect to a set A? Okay, so it is just saying that you, what all you need to add to A, to be able to generate S. Okay. And obviously we'll be using it in the case where A is a group. Okay, so what all do you need to add to the group, to get your entire semi group? Okay, because then it's like the group part, the rank of the group, we can solve that with, because the techniques to find ranks of groups will usually be very different. Groups are very special things. The techniques there will be very different, because in general we have seen that, for example, so the example was, let's say you want to find rank of GL and R. Okay, not for that. I do not know the technique for that, but let's say you want to prove something like the rank of every finite simple group. Okay, finite simple group is, at least I know about finite abelian simple group is 2. Okay, and the proof of that is completely group theoretic. So the proof comes from certain things. It results in the classification of finite simple semi groups. Right. So those techniques are very different from what we'll be trying to do. Our techniques, at least to find the ranks of subsemi groups of T, and will be highly combinatorial. That is what we will be looking at. right? So with that respect, we will move forward in by quotienting the group part and just focusing on purely the semi-group part to find the rank first of that, and then we can see if we can expect equality, right? Okay, so first let us come to certain obvious lower bounds again. Okay, so as mentioned earlier, we will be focusing on s mod g. Now, what's a lower bound? So the claim is that, well, the rank of s will be bigger than the rank of sorry, the rank of s will be bigger than the number of will be at least the number of rows and or the number of columns, right? So this is true because let's say you want to generate, so yeah, let's say you want to generate, so we know that s is like a triple, okay, where we have a row and we have the group element and we have the column element, and every element looks like this. So um this is what we know, right? Yes, this is what we know. And let's say you want to generate something like this which has an I here, so something in the ith row. Now, well, the idea is that if you want to do this, then you will need the star to be I, okay, because remember how the multiplication was. I mean, this is the multiplication was something like this. So this is this, and so I'm just sort of saying this again, um, in a sense that, yeah, just to catch up. And yeah, that's something like this, right? Then how would the multiplication be? You just take the ith row and the eth column, okay? And then you have this g, you get the p of, okay, you get p of lambda mu. So this is again some group element or zero, one of them, this something like this, right? So you get something in the ith row again, okay? And this we have also seen because it's an R class, and um, so on. Yeah. So the idea is that we need at least one element from each R class and each L class. Yeah. And so we'll need at least, so it will not be plus, okay, because you can understand, right? This will not be plus because some people think by this plus, but it's not plus, because if you this, you can, this is equal, so you can do with five things, right? You can choose these five things. So, and this, I'm saying that this kind of at least meets the criteria that you have one from each row in each column. Obviously, this may not be a generator. So at least we get the lower bound. This is obvious lower bound. Now we will be looking at those semigroups to start with in which this lower bound is actually an equality. Okay. There'll be what are known as rectangular bands, and even some other non-trivial cases where the equality holds. That will be really what we'll be doing next. Okay. Um, yeah, but before again we do that, we want to see the connection of the generating set of a completely simple semigroup in this form, which is written in this form. We want to see its interaction with the edge classes. Okay, this is the other description. So uh, if you want A to be a generating set, okay, then certainly A must generate the group part that's needed. Obviously, in our case, the group part will be trivial, but in general. Okay. And the other thing is that it must intersect every edge class. So remember, we just want it to intersect every edge class. A, or what you generate by A, must intersect every edge class. Just intersecting every edge class, the claim is enough. Yeah. Then you can generate the whole thing. Now you can try to prove this. Is just again pick an arbitrary. So it's just again you assume that A generates G. A can generate at least G and intersect every edge class. So you assume this feature, and then you try to basically pick an arbitrary element I comma G comma J, and you try to um, write it. You try to write it in terms of A. Okay, in terms of right. Yeah, you try to write it in terms of A. So what that would mean is that you try to write it in terms of G because A can generate G is in our hypothesis, and the other elements of A which are in some edge classes, but you won't have the choice over which element it intersects. So it can be arbitrary elements of edge classes, but you're allowed to use. So you're given one element each from every edge class, and you're allowed to use them to generate your I comma g comma j. Okay, so let's see. I mean, the idea is very simple. So the this I here. So what the way you would want to generate this is by using the I, right? Now we're not making a decision as to what we'll be putting in these two blanks here, keeping it like that. Okay, but for the group element, obviously there's a G here, so we're just taking a G here. Okay, and we are adding the J. So let's see what happens next. We just hypothetically multiply and see what happens. Okay. If you hypothetically uh, multiply this, right, then what sort of thing are you going to get? Right? You're going to get I, right, comma. Sorry, you will have this I, okay, but you will have a group part. So maybe we can just write this, right? Yeah. If you multiply this, you'll get I. That's fair enough. Um, you will get this star. Remember, this is group element, and you'll get P lambda 1 1. Okay, so this is in the lambda row and the first column of the P matrix, of the regular P matrix. Now, because P is a regular matrix, we can assume this is non-zero, and this is really the key. So, right, so we'll go ahead and assume that's non-zero, and then we have the G, and then we have the 1. Now, in the same way, you can continue and then again choose the I1 so that this is non-zero, right? So then your final product would look something like this. So remember, we are doing all this just to backtrack. We'll in the end backtrack and see if if we can choose these two things. Okay. So remember, you can make a choice on lambda 1 and I1, meaning you can choose which edge class you want to pick your elements away from, but you don't really have control over the stars because you don't know which element you'll be given from every edge class, because that's really coming from A, which is fixed. Yeah, so we have P lambda 1 1, and then we have a G, and if you just take this further, you'll get um, P1 I1, and you'll get star 2, and you'll get J. What do you get? Okay. Now, all that matters is this is non-zero. Now, because this is non-zero, you can always equate this to G by, right. So here is the thing. What are the things which you can change? Okay. So the problem is that maybe I have made a bit of mistake while when I was thinking about this, and thinking about this now, it's very clear that star 1 and star 2 are fixed. You can't change them. These are also fixed. You can't change them because you have picked the lambda 1 and I1 uh, for certain purpose. So we can't fiddle out too much with that. What we'll have to then change, which I have fixed initially, so that's wrong. What we'll have to change is G. We'll have to choose the G so that this thing is G. So let's call this G1. Okay. And so we want this to be G. So writing it here more clearly would be G1, P1, I1, star 2. We want this to be G. But certainly you can choose such a G1. It's a group, right? You can just invert these guys, take it that side, and that will be your G1 basically, right? So that's a description of generating sense. So we have proved that it's enough to have one element each from every H class, and enough also to be generate the group. These two things, if you have, then it's enough to generate every. This will this will play out. We'll see. So I think it will play out in the idempotent generated semigroups. Okay, right. So I think we can keep this for today. Now, next we'll be concretely looking at the simple semi, at those completely simple semi groups where equality holds, where the rank is equal to the maximum of the rank of the rows and columns, number of rows and columns, and we'll see that surprisingly large class of semi groups, not just large class of completely simple semi groups, not just you know those which are um, like whose P matrix is identity basically, but even others. Like idempotent generated semigroups, there also the rank would be the maximum of I and wedge. Okay. So we will, I think it's a good time to stop there and continue that the next time. Thank you.